Okay, so now that we've been introduced to the concept of Lorentz transformations and we've begun to see how they're going to be affecting our coordinates, we've seen how a Lorentz boost is going to take a stationary observer or stationary set of coordinates and boost it into an observer that's moving relative to that stationary observer. But let's now look at how Lorentz transformations are going to affect some other quantities that we know about, say the fall velocity. So the fundamental thing you should realise about Lorentz transformations now is that they are the coordinate transformations in space-time. And so when we transform any tensor, its tensor components are going to transform by a Lorentz transformation as we change the coordinates of our space-time. And so just as we could transform coordinates, remember we can essentially just think of the coordinate functions as living in a vector, and changing coordinates, we just use the Lorentz transformation to transform our vector of coordinates. But now we can, sorry, I think this is wrong there. But now we can equally use our Lorentz transformations to transform any other vector quantity or even tensor quantities. So in actually defining the Lorentz transformations, we realised the fact that when we transform the metric, essentially this has to leave the metric invariant, and so just writing the coordinate transformation law for a 0-2 tensor, realising the Lorentz transformations as the Jacobian, we can just realise the following condition. This would be just simply the tensor transformation law using our Lorentz transformation as the Jacobi matrix. And now this condition essentially says your transformed components have to be equal to the original components. We use this to actually derive and work out what the Lorentz transformations are. But now we just realise this is stating the fact that it is a coordinate transformation. But now we can use this to essentially use Lorentz transformations on any tensor, and we can use them to transform any tensor into different coordinate systems. So let's now look at something that we're hopefully getting familiar with, which is the fall velocity, which you remember was this now a vector, and just giving its components. We had that the time component was this thing, c gamma, where if you remember we've explored a little bit what this Lorentz factor is. We're going to see much more of that in this video. But if you remember, we briefly defined gamma to be dt by d tau, and then we saw that we can use the normalization of this fall velocity to arrive at the following expression for the Lorentz factor, where this v is now the coordinate velocity that appears in the Lorentz factor. And so we can see this fall velocity vector is somehow, or its components rather, being constrained because this gamma appearing in both components somehow depends on the value of the second component. And this constraint is really realised in realising that this fall velocity has a fixed length, and then this constraint effectively distributes that length over a space and time interval. But now let's explore this a bit more using the language we've developed for Lorentz transformations. So just keeping the definition of gamma in the back of our minds, because we're going to see more of this shortly. But now let's look at how we would Lorentz transform the fall velocity. Well, it's really simple. All we have to do is write now our new fall velocity, and the new hatted frame is going to be our Lorentz transformation multiplied by the fall velocity. It's really that simple. And of course, I'm just now working using the component language. I'm forgetting about basis vectors just to keep things concise. So now let's just see in general what this is going to look like. If we remember, we had that our Lorentz matrix, at least in 1+1 dimensions, the Lorentz boost only really affects the t and 1 space coordinate, and it had the following form. So this which I've written here is going to be the lambda x t, a boost between or a boost in the x direction essentially, and it's some parameterized matrix using this parameter psi, which I've said is the rapidity parameter. Okay, so to save myself a bit of writing and a bit of space, I'm just going to rename cosh and sinh, just giving them a shorthand. So I'm just going to rewrite cosh as a ch sub psi, and the same for sinh. Okay, so this is our expression for our Lorentz boost in the x direction. And now let's see what happens when we boost a full velocity vector. So rather than just boosting an arbitrary vector, I'm going to choose to boost the special version of this vector, or the rest frame version, in which this coordinate velocity is 0. So I'm going to look at what happens if I take a stationary observer's full velocity and I then boost that stationary full velocity. Well, it's going to be boosted into some frame which is moving relative to the first frame. And so we're going to expect that the boosted velocity, if that's the stationary velocity, I think I was using hats to denote stationary observers. In the stationary frame, the full velocity is just going to point straight up. This would be the c tau and x hat coordinates. But then when that velocity is boosted into some other frame, it's going to have to, well, first of all remain the same length, but it's going to pick up some non-zero spatial component, because we know that this new frame has to be moving with some coordinate velocity. So let's see this happening now. Okay, so I made an error when I first went through this, so I just had to rewrite what I had before. But now what I'm going to do is I'm going to now look at the stationary full velocity vector, which I'm going to call u hat. So this is the full velocity of a frame that's stationary. And so v is going to be 0, and then we've also said that in your own frame, this gamma, because your dt is d tau, this gamma is just 1. And so the stationary full velocity is just very simply c naught. So now let's look at what happens when we Lorentz transform this stationary full velocity vector into, or we boost it into some moving frame. So we simply need to compute the following matrix multiplication, simply boosting our stationary vector. So this is now going to give us, we're going to have a c cosh psi, and then a minus c sinh psi. So this is now our boosted velocity vector, u without a hat. And so immediately looking at this, we can see now that this space component is going to be non-zero. There is going to be some component of spatial velocity in the boosted frame. And now if we just think briefly about what cosh and sinh look like, if we just remember, cosh is something that looks like this, starts at 1. This is our parameter psi. Cosh is going to start at 1 when psi is equal to 0. And so if we boost essentially with 0 rapidity, this is just effectively doing no boost at all, because cosh of psi is just 1, and then sinh of psi at psi equals 0, sinh is 0 as well. So this is cosh, this is sinh. But then as we can see, as this rapidity parameter increases, this center psi is going to increase away from 0, and so the spatial velocity of this now boosted observer is going to increase away from 0 as this rapidity parameter increases. And I'll just briefly comment about the fact that there's a minus sign here. This is just kind of a convention, or not a convention, but it's just to do with how we think about these two observers. Essentially, we're saying that we're stationary in the stationary frame, and then we're boosting ourselves to a frame that's going to be moving with some velocity v away from us. And so we have to realise now that this is the velocity in the frame that's moving, and so we're going to essentially, in a frame that's moving, we're going to be leaving behind something that's stationary, and we're moving away from that object. And so from our perspective, remember this is now the velocity from the moving frame's perspective, it's going to basically see that stationary u hat vector moving in the negative direction as this frame moves away from the stationary observer. And that's simply why it's a negative velocity. Okay, so this is now how our velocity is going to appear from the perspective of our boosted observer. They're going to see our stationary observer moving in the opposite direction with a negative coordinate velocity. But this isn't really too useful by itself. But what we now need to do is go back and use our realization that this full velocity vector is normalized. It always has to have the same length, because effectively that length is fixed by the stationary reference frame. We can measure its length in one frame, and because of the invariance of the metric, this length has to be the same in any other frame. So let's use this fact now to learn a little bit more about this velocity transformation. So what we're essentially going to do is we're going to use a very similar argument to we did previously, where we're going to say that the length, now denoting lengths using these kind of modulus brackets, the length of our stationary full velocity vector is going to have to be the same as the length of that boosted velocity vector. And so whatever the length of our transformed vector is, it's always just going to have to be equal to the stationary length. And we've seen that this stationary length is always given by minus c squared. Okay, so before I compute its length, I just want to rewrite the vector slightly. If you remember, we had now the boosted velocity was given by c cosh psi, and then a minus c sinh psi. And now, if I pull out a factor of cosh, effectively it's going to do this. And now if you remember back to the previous couple of videos, we discovered that this thing, this c tanh psi, is simply defined as the velocity, the coordinate velocity. So if you remember, we derived this in the previous videos. And so I can now essentially just replace c tanh psi with our coordinate velocity. And just remembering we have this cosh psi still at the front that we're going to need to deal with. But now we can realise something quite nice if we just compare this full velocity with the general expression for full velocity. We can now just simply identify that this gamma parameter is now this thing cosh psi. Don't worry about the sign here. This v could be a positive or negative number, it doesn't matter. So it really kind of made more sense to just replace it with a modulus and ignore the sign. But don't worry too much, let's just leave it there for now. But essentially what we've now seen, or we can see quite clearly, is that this gamma is simply cosh psi. So let's arrive at this a bit more formally, rather than just simply comparing expressions. If you now remember, I'm going to use my normalization technique to compare the length in the rest frame and the boosted frame. And I'm simply now going to just compute the length of this vector in the boosted frame. So it's going to be minus the first component squared. So we're going to have a minus cosh squared c squared, and then plus the second component squared, so plus a cosh squared v squared, and then because this length is fixed, it always has to be equal to minus c squared. So all that's left to do is some algebra with this expression. So I'll just rewrite it. So I'm just going to factorise this cosh squared. So it's going to give us a v squared minus c squared. This is equal to minus c squared. Just rewritten and begun arranging this expression. And now if I divide through by now v squared over c squared and get rid of this minus, I can simply arrive at the following. And now if you remember, this thing over here is the Lorentz factor. We just need to rearrange it by dividing top and bottom by c squared. And so we've now essentially arrived at the realisation, if we take the square root, that cosh psi is this thing, gamma, the Lorentz factor that we define. This is now a way to reconcile what this psi rapidity parameter is. We essentially realise that the cosh of psi is our Lorentz factor, and so now using that we can rewrite a few things. We can rewrite, first of all, the Lorentz transformation. Or actually, briefly, I just want to comment, you could have arrived at this in a slightly different way if we just briefly revisited this formula and we wrote v over c is equal to tanh of psi. So we can define tanh psi to be this v over c, and now we can just really use an identity which says that the cosh of psi is 1 over square root 1 plus tanh of psi. This is just an identity. I'm sure you've had lots of fun working with these. But now we can just simply realise, well, tanh of psi is our v over c. Sorry, that's tanh squared. This is just an identity. But now we can realise v over c is tanh psi. And so we can just immediately arrive that the cosh of psi is this v squared over c squared thing. But rather than just relying on an identity to do the work for us, I find it's more illuminating to consider how, first of all, a stationary velocity vector is boosted into a moving frame, and then by using the normalization trick, we can arrive at this same formula. So now we can rewrite our Lorentz transformation slightly. If you remember, we wrote that the Lorentz boost between the x and t coordinates was this thing, the following matrix, but we've now identified that cosh of psi is simply this Lorentz factor, and now we can use some more identities to rewrite this sinh psi. Essentially we can realise tanh is sinh over cosh, and then essentially sinh is cosh times tanh. So sinh is going to be cosh, which is gamma, multiplied by tanh, which we said was v over c. And so the Lorentz boost is now going to look like this, which is arguably a much nicer and neater expression. We've got rid of all of these hyperbolic functions, but now we know and understand what these gammas actually are. Well, first of all, we understand it in terms of the Lorentz factor definition, and now we are starting to see how it's related to these boosts. So this is going to be very useful now going forward. We're going to start talking about how different quantities are going to appear in stationary and boosted frames, and this form of the Lorentz transformation is going to be very useful as it's quite nice and easy to work with. So I just want to now go over and summarise everything that I discussed today. So we revisited and looked at this idea of fall velocity being normalised in its own reference frame, and we've now seen how we can use our newly discovered Lorentz transformations to compare how this velocity is going to appear in our moving frame. And we've seen how we can boost this stationary fall velocity into a moving frame where it's going to pick up some non-zero coordinate velocity. And we've now derived, using the form of the Lorentz transformation, what this boosted fall velocity is going to look like. And then using our normalization trick, we're able to quite neatly identify that this cosh, the psi, this rapidity parameter, is somehow deeply connected with our Lorentz factor. And so in upcoming videos we're going to start looking at how these transformations are actually going to affect physical quantities like time and distance intervals. And we're going to see that this gamma is going to essentially control all of our relativistic physical effects. But for now we've just come up with or derived our coordinate transformations that leave the metric invariant. We've now identified that these coordinate transformations, or the boosts that we introduced, are now taking stationary observers into the frame of a moving observer. But now as we're starting to see, this Lorentz factor is starting to crop up all over the place, and it really is going to be responsible for the majority, or it is going to be responsible for all of the relativistic effects that we're now going to discover.